Thank you for your kind invitation to this workshop. I'm terribly sorry that I cannot be there in this time. Since I'm retiring of University of Tokyo in March, I have several duties to do in this month. So, but I'd like to talk about the synergy between PRIME and IRSF and Subaru telescope via SAND project. This is a new infrared spectrometer for exoplanet studies. So anyway, many congrats on the PRIME opening ceremony. And from ABC, which I belong to, and I explain later, Kotani-san will be attending the ceremony. So yes, let me see. Okay, so this is my plan for the today's talk. I'm talking about ABC. ABC is the Astrobiology Center, and also its parent institute, NINS. And ABC is working on exoplanet, and so I'd like to introduce what is the vision, mission, and value of ABC, and what actually we are doing. I would like to introduce. And especially, we are stressing the instrument for exoplanet studies. So I also explain it. So the main topic today is what is a SAND project and why ABC is involved for that, and what is the status and the development status of SAND. I will summarize these at my slide. And actually, the ABC, Astrobiology Center, and its precursor project at NOAJ have been involved with the IRSF camera, known as the Sirius camera, and its polarimeter instrument Servo. Maybe I don't have enough time to talk about these two instruments today. Anyway, so what is NINS? National Institute of Natural Sciences is not a university, but a so-called inter-university research institute consisting of 5 institutes. And I don't think inter-university research institute is common in foreign countries, but in Japan, NINS consists of 5 institutes whose measure is completely different, including astronomy and fusion science and biologies. Those are listed here. Let me see. It will show. Good. The pointer is here. Yes. And the current director is Kawai Sensei. She's a biochemist. And Astrobiology Center was established in 2015 as a cross-disciplinary collaboration among these 5 institutes. So ABC is to try to create some kind of new science as a new cross-disciplinary collaboration within NINS. And almost 10 years have passed from this establishment. And currently, we have 22 researchers, including leading researchers from overseas, currently 2 persons. And as a inter-university research institute, ABC develops and operates a most advanced exoplanet instrument. I will explain later. So its vision of ABC is eventually, I don't know how much time we need, but towards the creation of a universal study of biology in the universe in a very, very long time scale. But the current mission is in a relatively short time scale is we try to study exoplanet and life there. So what actually doing right now is advanced astrobiology field by combining multiple disciplines within NINS and promote research into exoplanet and life, both outside and within our solar system. But right now, the effort is mainly outside of our solar system. And The main difference from the university is as an inter-university research center, we develop a large-scale observational instrument that could be difficult for individual universities. We also hope to develop young researchers in the field of astrobiology. And we also hope to cooperate on Foreign Astrobiology Institute and invite foreign researchers. This is too much details, but we have three project office, so-called exoplanet exploration project office. This is basically for astronomy, and exolife search project office. This is mainly consists of biologists, but they are studying the planetary atmospheres and biosignatures on habitable planets. And another project office is astrobiology instrumentation project office. This is trying to build an instrument for searching life on this planet for next generation facilities. We are collaborating with foreign universities, including the University of Arizona and Washington, Caltech, and IAC Spain, and Max Planck in Germany, and also Kiel in Germany. And there are major network for astrobiology in the world. One is older NASA Astrobiology Institute, and its activity is still ongoing. But as an institute, it is terminated. And astrobiology network in Europe is also ongoing. One is IANA. We are also collaborating with this network. Anyway, so it's a kind of, we are trying to be a hub in Japan on astrobiology field. So this is a major instrumentation which ABC has been involved so far. One is infrared radial velocity instrument for Subaru telescope. And I'll talk about the SAND project, but the SAND is for SAO, and these two instruments are very similar. These are near-infrared high precision radial velocity spectrometer. Kotani-san, who is visiting South Africa for the ceremony, is a PI of this instrument. And another instrument is optical multi-band camera situated in the world, many places in the world. And this is, we call it Muscat camera. We have 4 cameras already spread in worldwide. And another is direct imaging for the 8-meter telescope, Subaru 8-meter telescope. That's an extreme AO instrument led by Olivier Guillon and Julian Rossi. And we also have a camera and spectrometer for this instrument, so-called CARIS, which is developed by the Princeton universities, including Kasdin and Tyler. So these 3 instruments, we are supporting these instruments on the Subaru telescope as other smaller telescope. Here is some science highlight which have been published recently. With the IRD instrument, we have discovered so-called exovenus, and for the comparative habitable planet studies, like the TRAPPIST-1 system. And that system we discovered is a Greece 12b, whose size is almost or a bit smaller than Earth. So it's almost comparable to Venus in size. And it's not exactly situated at the habitable zone, but it's rather the in that sense, it is similar to exovenus, but both are Earth-like planet. So it's very interesting why, like in the solar system, why Earth-sized planet like Earth and Venus has a different path. So that's a good target for JWST2. So we are proposing to study the atmosphere with this JWST. With the Muscat cameras, we are following up the test planet exoplanet target candidate and collaborating with Guillaume. I think the one of the publication, famous publication, is a discovery of Speckles 3b. This is also Earth-like planet around M6.5 star. It is recently published. With the SCEX-AO, since with the Subaru telescope, we can make use of a very large aperture as large as 8 meters. So adaptive optics is very powerful instrument. So our previous adaptive optics is about 200 actuator or DM system, but currently we are upgrading to the 3000 extreme system actuator adaptive optic system. So the direct imaging of large planet, Jupiter planet, are becoming more easy, especially combined with astrometry with Gaia and Hipparcos. We can predict it, we can expect which planet are more likely to have a giant planet. Such kind of target limited observation is now available with this system. So the recent discovery is a very efficient direct imaging discovery of HIP 99770B, which is published recently. So for these three instruments, ABC has been heavily involved. Okay, so related to the SAND project, I would like to very briefly introduce the IRD project. This is a high-dispersion near-infrared spectrometer fed with fiber, and resolution is about 70,000. So that can avoid many atmospheric absorption lines at near-infrared. We have two detectors which can cover the very long wavelengths from YJH band. And we also use laser frequency COM covering almost all the same wavelength range of this spectrometer, so that we can have a very accurate radial velocity measurement at near-infrared. And we can actually use a multimode fiber, but if necessary, we can also use a single mode fiber, which is free from modal noise, so-called modal noise. But usually we are using the multimode fiber right now. And its instrument has been used almost more than 6 years on the Subaru telescope. And for these 6 years, one target which you are monitoring is as accurate as whose radial velocity we can measure as accurate as 2 or 3 meters per second. So that is enough to detect Earth-like planet around M stars, not the G stars. So this kind of infrared radial velocity is very powerful on the 8-meter telescope, but for the long-time monitoring and more frequent monitoring, I think the prime telescope will be very powerful for this this kind of infrared radial velocity studies. Another involvement is of ABC is we have supplied polarization and mask optics for this very complex coronagraph in space. And Japanese people are participating in the coronagraph activity program. And another aspect is very far from the astronomy. But since this is ABC is an interdiscipline institute, we also try to attract biologists so that they can study the biology on the possible exoplanet, habitable exoplanet. One is trying to predict what kind of photosynthesis is possible on exoplanets around red dwarfs, and our prediction is red edge, it does not change from that on Earth. So the red edge of exoplanet can be universal. That's one of our predictions. And we also calculate the fluorescence of exophotosynthesis. I think this is the first time, but this is a very challenging observations, and it will be observational evidence will be difficult to directly in the near futures. So these are mostly theoretical predictions, but for the other extreme condition like the Antarctica, we can actually take the sample and what kind of photosynthesis is going on. And it is known that some of the algae using the infrared light rather than the optical light for the photosynthesis. And one of the astrobiology at the ABC member actually studies its molecular constitution and try to explain why such kind of algae is using the infrared light rather than the optical light for the photosynthesis. So this is a theory and this is a kind of experiment, but this kind of collaboration with biology and astronomy is actually taking place. So I will explain the SAND project then. So the development team is shown here. This is another near-infrared high-dispersion spectrograph to be installed on prime telescope and can be fiber linked to other telescopes, including IRSF and other telescopes. This is a highly stable instrument for measuring the radial velocity. And the main target will be the exoplanet, but there could be other applications. So since we have many experience with the Subaru IRD, that experience can be used for the development of this instrument. And the scientific background of this instrument is we have several reasoning. One is studying how the giant planets are formed. For example, there are major theories for explanation of the giant planet formation. One is a slingshot model, another is a type 2 orbital migration. And but in order to distinguish these theories, we need a long-term monitoring of the radial velocities for the young clusters members. So this will be, I think, more easily done in the southern hemisphere, where many young clusters can be observed from the southern hemispheres. Another is, this is not always necessary to be the southern hemisphere, but we also want to systematic search for the habitable planet around M-stars. So this is similar to those already ongoing on the Subaru telescope. But if we can use a prime telescope time, not only the relatively short time, but for a long time, as long as for many 10 years or so, we can monitor various kind of M stars. I will show the real example later. So high frequency of presence of the M stars is a good reason, and low effective temperature is near-infrared is very strong point. And since the central star is low mass stars, we can detect actually as low as Earth-like planet. Okay, so another point why we are doing the near-infrared is young stars. If we want to the young stars and M stars, sometimes sunspot on their surface will become a problem, and it will mimic the radial velocity by the planet, real planet. But at the infrared wavelength, that effect is mitigated. And for especially young stars, and both young stars and M-type stars are faint at visible. So we can study the radial velocity at those targets at near-infrared better. So this is a specification of the sound. We can cover the relatively shorter wavelengths of the near-infrared, so-called ZY band. And this band is also, some of the lines are very useful for the exoplanet atmospheric studies. The resolution is about 70,000. And the big difference between the Subaru telescope and sound is we don't use adaptive optics. We use image slicer for this instrument. So the diameter of the fiber is 2 arc second. So this is will fit 1.5 arc second seeing at South Africa. Efficiency is better than compared to the IRD, which is only 1% or so at 1 micron. Since we are using the image slicer, I think we can achieve the 8%. And our simulation predicts for the M-type stars with a 30 minutes exposure time, we can attain the 2 meters per second for nearby stars, for nearby M stars. So we'll start with prime telescope, but eventually we can link this sound to the IRSF, or if necessary, we can even link to the third telescope. The distance is 200 meters and 300 meters, but the fiber link is possible in principle. Since the prime is a first prime focus instrument, telescope, we need to switch the prime focus to the fibers. So the fiber injection module is we need to prepare. And actually it is almost ready, and we can install this kind of fiber injection module to the prime telescope, and that can be inserted to the prime focus and distracted to the prime focus. And this is a shell spectrograph, and its optical design is very similar to that of IRD. So we are pretty sure this optics works for sound too. This is the optical assembly of this instrument, and DUA is already fully available. So we are still assembling, but we hope to bring that instrument in this year for the early next years. So with this instrument, we can study nearby M-stars like this one. This is a list of the possible available M-stars distance, and this is a R3 precision that we can achieve. So if we restrict, say, the accuracy is 5 meters per second, we still have hundreds of M-stars for monitoring. So with the accuracy of, say, for 2 meters or 3 meters per second, we can certainly detect some of the iceberg of the habitable planet with possible water. So I think that's almost, yes. This is just, I think, already introduced. We also operate involved with IRSF telescope with Nagoya and Kagoshima and Kyoto universities. And recent progress is we now have 5 bands simultaneously, JHKS and I+G. So this is Orion, center of Orion. So you can see, and these 5 bands are simultaneously now observable. So this is a summary. ABC is an inter-university institute, and we are developing the sound spectrometer. So we hope to keep collaborations with SAO through this IRSF and the PRIME project. Thank you for your attention.
Thank you very much. Are there any questions? Let's quickly check online. Yes, David.
That was a very nice talk. I'm just wondering, I remember many years ago talking with Katani-san about the possibility of using salt to feed the 502 sand. Of course, the issue there is the different plate scale and the fact that you wouldn't get the same resolution with salt as you would with a smaller telescope. So I was just wondering, I mean, he had some ideas to maybe improve that, but even if it was lower resolution, it might have some applicability to other sort of science outside of exoplanets. I just wondered if you had any comments about that.
I see. Okay, so for the low resolution spectrometer, I think it's still under development with by Nagayama-san. So for the prime telescope, we are seeking for the radial velocity studies for exoplanet, but for other applications, I think the low resolution spectrometer is still very powerful instrument. So that could be attached to the IRSF, I think.